You know, the problem with a super accurate clock is that I sit there and watch it. 5 o'clock straight up. My phone turns to 5 o'clock, so there you go. What happens when you get a synchronized clock? Synchronized clocks solve a lot of problems in distributed systems, but they create a new problem. That is, now you have to synchronize the clock. I believe, if I remember correctly, Google spent $500,000 per data center to implement the Chubby Lock Manager. It was a synchronized clock-based consensus mechanism. And then in the end, what they did was, because they knew their clocks were super accurate, all they did was just delay sending the messages. And that created enough certainty. It's kind of a strange concept, but it's a question that's come up a couple of times this week, so I thought that it would be a nice way to segue into the class. And that is, what does it mean for something to be linearizable? And the idea behind linearizability is that you have a way of establishing a sequence of events. The reason that we end up using replicated logs is because replicated logs create a linearized system. What we don't get with linearizability is a guarantee that any possible linearization of events will lead to the same outcome. Somebody asked about the difference between deterministic and linearizable. Deterministic means it doesn't matter what order we apply these things in, we're going to end up with the same answer. And that's a different requirement. Linearizability just simply means that from the viewpoint of the external world, something happened in a particular order and it never is going to change. Deterministic doesn't mean that it's not that we couldn't look and see different values different times, but eventually we're going to see the same value. And the reason that that distinction is interesting is because one of the kinds of data structures that people have created to build distributed systems are called CRDTs, conflict-free, I don't remember. It's the data structure that relies upon operations that can be performed commutatively, and thus we can change the order of them, like addition. We can change the order of those things, and if we add the numbers in different orders, we end up with the same result. The specific order we do it in becomes a linearized state. In other words, what does the external observer see? See, this is the distinction that we keep going back and forth on, is what's visible outside the world versus what's visible inside the world. Because our service has an interface. Our clients say, please do something. Put a value into this key. What we don't want to have happen is have a client put a value into a key, have it do a get on that key when no one has changed anything on that key, and find out the key's changed. Could you build a service that did this? That wasn't a rhetorical question. It was actually a genuine question that I think you should be able to answer at this point. At least I hope so. I see nods of heads. One person nodding yes. Do I see anybody nodding no? I may have you guys duke it out. Amazon's S3 service provides exactly this kind of functionality. Years ago, I looked at using S3 for a project and concluded that if I never rewrote a key, it would be great to solve that particular problem, because there were only two things that could happen. One, I could read the key and I would get back a not found, or two, I'd read the key and I'd get back the only value that key ever had. The moment that I mutated it again, all bets were off. I could now get any one of those three. And the reason for that was because they provided a guarantee that eventually everything would become consistent. Eventually, in the fullness of time. Right. Kind of like, eventually this lecture will end. It seems to drag on forever. All right, now we get to boring stuff. Logistics, things changed there. Jonas does not have office hours on Thursday because he is affected by, what is it, Makeup Monday, I guess it's called. That's what he was calling it. So Makeup Monday, which is Thursday, means that he has a conflict. So he won't have office hours this Thursday, but he will move to his new office hours time next day. And we will have class next week on Thursday. Lots of things upcoming. Let's see, don't forget that the Design Project 1 implementation report is due at midnight. That is different than the code deadline, which just passed a few minutes ago. You'll notice I staggered them, and I'm going to keep staggering them. That's because I want you to have some time interval, even if it's only a few hours, to think about what you learned rather than focusing on writing code. How many of you were writing code up until 5 o'clock? He's got his laptop there. He's going, I can submit this one more time. I can make some tests pass. It doesn't matter. It's really interesting to see how this plays with your heads because you've been so trained to think about how does my code work? How does it pass this test framework? That's what you focus on. But that's not what I wanted you to focus on. The code was there so that you could say, I've got a set of instructions that tell me what to implement. How good was this set of instructions? It's like getting a piece of IKEA furniture and trying to assemble it. I don't know, has anybody ever taken IKEA furniture and tried to assemble it from the pictures? Is that frustrating or what? Usually by the time you're done, you figure out exactly what it is that it meant. You're ready to put another one together. Of course, you don't have another one to put together. How many of you found yourself focusing on passing the tests rather than implementing the design? Several people. How many of you just didn't even bother to implement anything? You just submitted some code that compiled so you could get credit. There you go. Somebody who's actually honest. A couple people. I actually saw somebody who modified the code so it didn't compile. Like, dude, we gave you code that compiled. It passed no tests, but at least it compiled. And then lots of people didn't actually read the instructions. It said, oh, by the way, you have to build a zip file. See, one of the concerns that people have when they're using DS Labs is that folks are going to try and hack the grader. I don't have to worry about that because I don't care. Hack the grader, go ahead. But the infrastructure is already there. So it has a manifest of what you can submit. So that's why I use a submit script because it puts it together in a very particular format. The files that are supposed to be there are there. Nothing's missing. Nothing extra is added. The extra is added thing is where people worry. There's potential vulnerabilities when you take random code and insert it into a container and then unpack it and try to get it to compile. Okay, fine. What always amazes me about people who do that is I think they spend more time hacking the system than they do if they just implemented the project in the first place, but sometimes that's the challenge. That's the fun part. There's quite a few things due next week. Don't forget Thursday at 5 p.m. your design project is due. For Design Project 2, that's the Paxos implementation. And what are we going to be talking about today? But another round of Paxos. So this is a timely conversation for those of you who are still working through the design. It looks like about half the class is in groups and about half the class is doing the lone wolf thing. I forgot to plug it in. Not that I've ever done that before. I thought that was interesting. There's things due both on Tuesday and Thursday next week. Don't forget, next week you'll have feedback, your feedback on Design Project 2. So we're iterating over this design process. Hopefully, you've now gone through this cycle and you're starting to see that, hey, I'm already doing a better job of building those designs. Or you're just submitting crap and nobody will care. We did finally get the list of exemplar designs. I don't know if anybody took a look at those, but these were designs that we thought stood out as being pretty good. So hopefully that will give you some guidance into where you might want to take your own designs. Again, design projects 1, 2, and 3 are really just submit something, fine, go through the process. If you skip that, what you're going to end up doing is cheating yourself, and you're going to make your capstone project a little more difficult to do. So when you're forming groups for your capstone project, which will happen relatively soon, you might want to be asking your prospective teammates to see what their designs look like. Guessing that there's going to be the 8 designs that we identified, there's going to be some people who are going, yeah, it's mine. Of course, you could lie and say that was yours too. Let's talk about failure. This one is GitLab. Very straightforward one. They had increased database load. There was an anti-abuse feature that caused a GitLab employee to be marked as abusive, which caused them to start deleting the stuff from that employee. Bad things happened. The secondary replication, and I thought this was a great follow-up to primary backup replication, because this is the quintessential problem in replication of any type, whether it's primary backup or it's Paxos or Raft or so on and so forth, is we end up garbage collecting. Because when we do log replication, what happens is eventually we get to a point where we realize everybody knows about these log entries. So I'm not going to keep them anymore because they take space. When is it safe for me to delete my log? What am I trying to guarantee? I need to guarantee quorum. I need to guarantee that any quorum is going to have a copy of that data. So in essence, what ends up happening is that I can truncate my log when I know that the quorum will be preserved. Well, in a primary backup, not much of a quorum there, is there? You can't delete from the primary's log until the secondary, the backup, has actually applied the change. They got it wrong. Oops, sorry. Hate when that happens. So they tried to do a manual resynchronization of the primary to the backup, and they deleted the secondary's backup and copied the primary to the secondaries, but the copy routine failed, and now the copy routine was blocked waiting for the data transfer, so they didn't get any feedback, so they didn't know it had failed, and this could take hours. So there's no monitoring. You don't know. You ever copied files? You see the choochy little animation that shows the rate at which it's copying. Well, we didn't get one of those. At least if we'd seen that choochy animation, we would have said, hey, it's not moving. Sometimes that happens. And then you can take action on it. But here it was like a command line utility. We don't give that kind of thing. So somebody then tried to clean up the secondary, but accidentally deleted the database on the primary. Do you see how bad things can get? This could be your job 6 months or a year from now. Then they couldn't find their backups in S3 because it turned out that their backup process was using an old version of the backup tool that wouldn't back up newer versions of the database because the version didn't match. Oh my gosh. Does it get any better? And nobody noticed. This is the problem with backup. No one notices the backups are broken until they need to restore. And at the point you need to restore, you find that the backups are broken, you're dead. Oh, and they didn't have Azure disk snapshots because they were using Azure. They didn't have disk snapshots enabled. Yeah. Like one mistake after another. That's a really good question. What would you think maybe somebody should do to make sure that these things don't break? That like monitors things and reports anomalies, like having a backup script that doesn't tell you when the backup fails because there's a version mismatch. Maybe that's just a bad idea. My sense is there's a whole series of failures here, not just one. And this is not uncommon. You see these cascading failures because you have one rare condition after another rare condition after another rare condition, and then you find out that all of these things are breaking, and now you have serious data loss. In the end, they restored from an LVM snapshot, logical volume manager snapshot. So inside of the Linux server that they were running, somebody had enabled LVM and they had mirrored something, or they enabled snapshots. So they were able to get back to the old copy of the database, but it took them 18 hours to fix that. Multiple levels of redundancy failed. There's a really cool write-up on this. I don't want to go into more detail on it, but it's a really fun example because it is primary backup replication that went wrong. And then, remember what did I say when, the primary goes down and the backup's not available? What do? You basically throw up your hands and go, I don't know what to do. I'm going to call an administrator to deal with this stuff. Somebody in DevOps will handle it, right? And then we find out the DevOps people, I don't know, they were smoking something. And they weren't sharing it with the database, that's for sure. We're going to talk about Paxos Made Simple. And I picked the Paxos Made Simple paper because I think that of all of the Paxos papers, it is easiest to understand. Lamport is pissed when he's writing it. It's very clear that he's annoyed that people couldn't get it from the part-time parliament. But somehow people got lost in Greek legislatures and all the contracts and ledgers and priests. So you can go to Paxos and you can read Paxos Made Simple. It's only 5 pages. Did anybody read it? It's not very long. He really was just like, okay, fine, you people are too stupid. I'm going to just sit down and write it down in a paper. And he walks you through the logic of what Paxos does. What are you doing in Design Project 2? You are building a Paxos system. Not as simple as this. It's actually based on a different paper. If you want to see, I did a lecture on this last term. And the questions that came out of that afterwards really helped me understand why people get confused by this stuff. Because Paxos Made Moderately Complex, PMMC, is the paper on which DS Labs is based. They combine the Paxos protocol with a somewhat optimized implementation. And the optimizations make it less understandable, but better performing. What is the consensus problem? What is the problem we are trying to address here? We have a simple model. We have asynchronous communications. It's not Byzantine. Nobody's lying to us, and we don't get corrupted messages. So that's a simplifying assumption. We don't have a fixed clock. Sorry, we don't get the benefits of having that synchronized clock on the wall. Messages can be lost, delayed, reordered, duplicated, but not corrupted, hence the non-Byzantine thing. We are guaranteeing safety. This is a strong safety system. What that means is only proposed values can be chosen. That kind of relates to the Byzantine idea. You don't have things spontaneously pop up that says, hey, by the way, this is the value that got chosen. And there are people like going, I didn't see that proposal. And if you think about it, that kind of makes sense because we need to have that quorum intersection. And if it wasn't proposed, nobody else saw it, so we don't have a quorum. Only a single value is chosen. Now, we're going to, of course, perpetuate this at some point by allowing additional rounds of proposals. But we're going to start off. We're just trying to make one decision, just one. We want to agree on one thing. What are we going to have for dinner tonight? And finally, a process learns a value if and only if it has been chosen. So remember, we're only trying to choose one value. Now, it's pretty easy once we have that one value chosen and we have a quorum on that, we can then move to another proposal and choose a second value. We're going to be able to perpetuate that onwards, but we're going to start off by just choosing one thing. That's all he sets out to do in this paper. He uses very specific terminology. One of the things I have found very confusing in trying to talk about the different Paxos papers there are is because they use different terminology for the same things. Because they don't like the terminology that anybody else uses, so they choose different terminology to confuse you even further. I don't know if you've ever seen people do that. They try to pick words they think are more descriptive or better than what everybody else was using to describe something. And initially you look at them and you go, what are you talking about? So I'm going to stick with his terminology here. This isn't priests and all their contracts and ledgers. This is proposers, acceptors, and learners. And each of these components has a very particular role in reaching a decision. A proposer is responsible for proposing. Gosh, that's really deep. The value of proposals only come from proposers. Those values are submitted to the acceptors. We're going to talk about those in a second. Proposals are identified by some number. The definition of number here is very general. In essence, what they really do is they think of strings as being numbers. Right, fine. I can take an IP address and realize that it's 32 bits long, and so I can represent it as a number, or I can represent it as a string that has 3 dots in between octet. It was last week, and I went and looked this up, and I confirmed it. In fact, in the 1970s, Lamport published a paper, one of his very first, because he's in his 70s now, so that would have put him in his 20s, probably not much older than you were at the time he proposed this, something called the bakery algorithm. And the bakery algorithm was an algorithm, and that link is actually live. It points to the Lamport bakery algorithm, which is a really old paper. It's literally a scan of the original journal it came from. And it's like 3 pages. It's just a description of how in a concurrent system you can provide for mutual exclusion. And the reason he called it the bakery algorithm was because it was what happens when you walk into a bakery with the little numbers, that you pull a number and you wait until your number is called to get service. Order whatever delectable bakery item that you want that day. Except that when you read the problem statement, it's an awful lot more like what we're trying to do. It's just that it's doing it in a simpler domain. See, these processes are all running on the same computer. So we have a fate sharing that we don't have when we move into a distributed system. It's not identical, but it struck me last week as I was talking about it. I'm going, this sounds like the bakery algorithm. And I had to go look it up. And indeed, it's very similar. The thought process behind it is very similar. And the bakery algorithm is a little bit easier to understand. So when he comes back with the Paxos protocol, what he's in essence doing, he likes allegory. So he used bakeries last time, and this time he used Greek legislatures. They're very similar. How do you deal with the possibility that 2 different processes get the same number? And he disambiguates them in exactly the same way we do in Paxos. He uses the process ID. In Paxos, what we're going to do is we're going to use the server number, server ID. And we're going to just glue them together, so it becomes 5.2. That way, if you and I choose the same number, 5, the thing that will distinguish our values is going to be the .2 or the .3, because I'm going to have a different process ID than you are going to have. So we have some way of distinguishing my ballots from your ballot, just like we have some way of distinguishing the order in which these 2 numbers were chosen in the bakery. It was kind of cool. It was like, wow, okay. Except that the bakery algorithm is a little bit easier. It's not trivial to work through because he still has the same asynchrony model. But at least it gave me some framework for realizing this isn't a problem that he just woke up one morning and said, hey, this is the way to do it. It's like literally something that was sitting in his head for 20 years when he came back and he came up with Paxos. So I sold some slides from last term, which I stole from class at Georgia Tech with permission. A proposer sends a prepare message to the acceptors. Now, that term prepare is a very specific term of art in databases when you talk about transactions. And essentially, that's what he's thinking of this as. This is a form of transaction. He says, are you prepared to accept this value? And he sends that to some subset of the acceptors. Not necessarily a proper subset, so it could be all of them. And normally, in the real-world implementations, that's what we do. We broadcast them out, or we multicast them out, or we send them one at a time to all of the acceptors. Depends on the network. An acceptor gets to vote on the proposals it receives. That's its job. Oh, and it has to remember them. It has to remember what it did. It has to remember that in a persistent fashion. What that means is there's a little database there. Just one value. The acceptor will accept a new proposal if this is the first proposal it's ever seen. Hey, you're the first proposal I've actually seen, so I'm going to accept it. Because I can't possibly conflict with anything at this point. So I'm willing to take your value. Or the new proposal contains a number greater than the previous accepted proposal. That's the proposal number, not the value. We're not comparing the value here. We're comparing the proposal number. You'll note what is not here is if it's the same number or below. Now, if it's the same number, it has to have the same value, because it's a retransmission for whatever reason. Remember, packets can be duplicated. We don't have to respond to those. We've already received it. We could respond to it. That's perfectly acceptable too, because our packets could have been duplicated as well. That becomes an issue for the implementation, not for the protocol. So in this case, accepts means I'm going to send a message back to the proposer saying, I'm willing to accept this message. But that is not a decision yet. It's just a proposal. Once a quorum of acceptors have sent back an accept message to the proposer now gets to send a commit message that says, I have a quorum, this is the value we've chosen. So the proposer sent a prepare. The acceptors said yes, some subset of them, some quorum of them, said yes, I agree. And now the proposer gets to send a commit message. Basically, the proposer is telling the acceptors, you have agreed to this value. And now we know what the value is. A quorum has agreed to this value. And based upon our definition of quorum, well, maybe that message that came on when I turned the projector on earlier today that said, it's time to replace your bulb, was just an advance warning. It's like a very bad strobe effect. Not sure what I can do about that, but we'll persevere for the moment. If this keeps doing this, I don't know, I'll figure something out. Now see, once the acceptors learn that a value has been accepted, they can tell the learners. There is this interesting time between when the proposer learns that the proposal has been accepted and the acceptors learn of it, where the proposer could die. But we've got a quorum, so anybody else who goes and asks will be able to determine that we had a quorum. That's going to be part of our recovery. But why do we have these learners? What is the function of the learners? This is what I started with today when I was talking about what is externally visible. Notice that a learner cannot learn of a decision until it has been accepted. So the reason we distinguish the learners from the acceptors versus the proposers is that the learners are firewalled from seeing what's going on between the proposers and the acceptors. The learners only learn things that have actually been chosen. That's why we put them in there. That guarantees that a client who only can find this out from the learners, the client will never see an inconsistent internal state. Where we're having this conversation trying to decide what we're going to have for dinner, we're not going to let them know that's going on. That's why we do it in this way. And we can walk through this, and that's what the paper basically does. It says, if things come unraveled here, this is what's going to happen. This is how you're going to guarantee these invariants. His invariants are, in essence, what he's saying has to be true in order for this to be safe, which is a very formal way of walking through the failure cases and saying, how am I going to deal with that failure? I just gave you one. The proposer dies after it has received enough votes to accept, but before it's told anybody. So the acceptors don't know that it's been decided. But all of the acceptors have now voted for enough values. So we have an acceptance, so we can find it through the quorum. The learner then only sees accepted proposals. The specific mechanism of how the learner learns isn't actually formally defined, but Lamport does provide us with some suggestions. He says acceptors could push their values to the learners. That way learners learn quickly. So the gap between when the decision was made and when the client can be told about that decision is narrowed or made smaller. Remember, just one value. That's all we were going to agree on here. We didn't decide that we were going to agree on multiple values here. It's just one value. So we're never going to have another value here. But that's not very useful. We're going to want to extend that. But let's start with the simple case, because has anybody ever done proof by induction? He does a proof by induction, and this is exactly what he's doing. He's saying, hey, I can pick one value. And here, I can show you how if I can pick in values, I can pick in plus one. And I can do it reliably with safety. That is exactly what his safety argument is, his safety proof. Is it a proof by induction? So this is the one case. Nobody else is going to propose anything else, because we're only going to agree on one value. We're done. Learners can query the acceptors. Learners can learn from each other. Learners could even ask the proposer to issue a proposal. That's one possible model. In fact, when you look at his implementation description, he suggests that what you want is a distinguished proposer and distinguished learner. Because if the proposer and learner coexist in the same process, the learner will know immediately when the decision has been reached. So that's an optimization, but it's not part of the protocol. It's just an optimization to the implementation of the protocol. The protocol clearly separates these roles because it makes it easier for us to reason about and to convince ourselves through a formal proof, which he provides in the paper, that this is actually safe. But choosing one value isn't enough, is it? We've got a one-entry database. We can write to it once. We want to choose another value. But now we want to choose a value for some other key. Or how about this? How about if we choose another value for the next entry in the log? So we'll make this a log. So the value that we agree to is just that one value is what goes in this entry in the log. And now the value that we agree to next is the next entry in the log. And that's actually how we're going to scale this thing up. The reason that he wants us to use a distinguished learner and a distinguished proposer is because what his basic algorithm lacks isn't safety, it's liveness. Sacrifices liveness in favor of making sure that we never have inconsistency. But in liveness, the problem is that we never achieve consensus because we keep getting new proposals. from different proposers? Well, if we only have one proposer, we don't have this issue. And so that's back to the lecture from last week, which was, gee, let's just elect a leader. That would be our one proposer. Simple, except that we had problems with that. It was actually kind of hard to make that work right. But we have a protocol that safely accepts or adopts one value. So what one value should we start by adopting? Zero? That would be a value. What? What value? What? Not, I wasn't trying to ask for a specific number, I guess. What value? What are we trying to decide first? Who's the leader? We have a balloting protocol. We have a mechanism for picking a leader. Gee, choose a number between 1 and n, where n is the number of proposers in the system. We're going to elect one. And the best part about this is it kind of is like one of those models last week, which was you had two different groups. So here we have candidates, and here we have electors, and they're not mixed. So our candidates are the proposers, and our electors are the acceptors. So we have proposers, acceptors, and all they want to do is pick who the distinguished proposer is going to be. Okay. Not a big step now. And the big step was trying to walk through and understand what that flow of control was and why it actually provides us with the guarantees that we need. Now, I have a slide in there too for just showing you that the learning, of course, occurs after the value's been accepted. There are interesting edge cases here where we can have proposers with different values and we can only choose one. Now, what's interesting is that we can race. This is the whole thing I just got done saying where we have a problem with liveness, right? So we can race. So I propose that I'm the leader. You propose that you're the leader. And we talked about this last week, talked about it before as well. Challenge is if I sit there and shout, I'm the leader, and I get one vote for myself, mine, and you vote for yourself, and you vote for yourself, and she votes for herself, we don't end up with a leader. And so how do we reconcile that? How are we going to end up with a leader? What we're going to do is we're going to stagger. Because what we don't want to have happen is we don't want all of the proposals to go out simultaneously. We don't need, from this perspective, let's step back from the problem for a moment. Does it matter which of the leaders or which of the proposers becomes the distinguished proposer, aka the leader? No, they're identical. These are replicated state machines. They're identical. So from our perspective of the problem we're trying to solve, we don't actually care which one wins. Okay, fine. Then the one that volunteers first, assuming that it's not partitioned off from the network, perfectly acceptable to us. So how do we guarantee that it's not partitioned off from the network? What guarantees that the leader is not partitioned from majority of the majority of the network? It has to have a quorum. It cannot be elected if there's no quorum. If you have a quorum, no one else can also have a quorum. That was our definition of quorum. I've tried to avoid the term majority. It creeps into these conversations frequently. Read these papers, they talk about majorities, because majority is the easiest of quorum for us to understand. But as I've pointed out, quorum is more general than a majority. A majority is an example of a quorum. But I'm trying to be really careful here to use that term quorum because it turns out that using the more general meaning, the more general concept of quorum leads us to interesting distributed systems that most people are not even thinking about because they've got the majority model in their heads. So I'm trying to make sure you don't get that bad habit to begin with. So we have a leader election protocol now. Great. How do we now replicate our log? See, what we need to be able to do is distinguish one leader from another. See, normally what happens is once we've selected a leader, that leader remains the leader until such time as somebody thinks the leader is dead. Why would we think the leader is dead? Because they died. Oh, okay, that's interesting. A tautology is something that is tautological. Thank you. Very deep. You're building a Paxos implementation. You're designing a Paxos implementation, which is probably almost done at this point because it's been a couple hours. How do you determine the leader has died? What might lead your proposer to think that the leader, the distinguished proposer, has terminated or is not available? We're all afraid of saying it. I can sit here and wait. How do you decide when something is dead? When you try to hit a website and it doesn't respond, what do you do? What do? You just ping it. Send a message. Hey, are you there? Yeah, I'm here. Okay, great. So if I stop hearing from you, at some point I'm going to say, I don't think you're there anymore. That's it. It wasn't a deep question. It wasn't intended to be like this soul-searching kind of thing. It was like, wow, this should be pretty obvious net by now. So I've failed. A heartbeat, a ping, a message. I haven't heard from the leader in a while. Maybe it's because there's just nothing for them to propose because the system is quiet, in which case then I do a ping, I get a response back. And the reason I might do that is because I want to protect the liveness of the system. If I'm not hearing proposals and I send a message, okay, so why would I hesitate to send too many pings? There was some conversation about this last week. It creates a lot of network traffic. Got 10,000 proposers, and they're all like pinging each other, going, even if one of them, each one of them is pinging the distinguished proposer. That's a lot of network traffic. And if I'm hearing from them on a regular basis, probably not very useful. So, I'll set a timer. And I'll say, hey, okay, it's been, 25 milliseconds, to pick a random arbitrary number that the DS Labs folks like. I haven't heard from you in 25 milliseconds, so I'm going to send you a ping. Well, now I'm at least minimizing my impact on the network, because if there's lots of proposals coming in, I'm hearing from the distinguished proposer all the time. The leader's constantly got me doing things. I don't have to worry about them being dead. I don't have to be proactive and do active pings. That's an optimization. The basic idea is I use some sort of liveness detection mechanism to decide if I think the leader might be gone. But I can't tell if the leader's gone or the network between me and the leaders. So I haven't heard from the leader for a while. I ping him. The leader doesn't care if I'm dead. If I'm just one of the random proposers out there, the leader doesn't care at all. And you'll notice that the leader and the acceptors aren't pinging each other either. All the leader knows, proposer, the distinguished proposer, all they know is I send these things to the list of acceptors and I either get a quorum or I don't. If I get a quorum, I got a decision. And since I'm the leader, I'm the only one who's making a proposal right now, I don't have to worry about somebody else coming in and making an additional proposal. So in essence, I've got that really optimal world that I started with, which was if all you have is just a single proposer, you don't have any race conditions, you don't have any problems here. So all we have to do is deal with the boundary condition between leaders. That's when it gets complicated. How do I distinguish when there's been a leadership change? What distinguished the leader election? I can go back over it again. Barely see it. What did I do? I sent a message. What was one of the characteristics of that message? Sorry? I heard somebody mumble something. You're being shy and bashful, or I'm not doing a very good job. There's a proposal number, right? How do I know who the leader was? There was a proposal number. That was the highest proposal number that was used to elect them. You will see this in some of the papers where they talk about the ballot. You might see it called an epoch. But in essence, it becomes an identifier that says, this is the leader. Using the ballot they were elected on is a perfectly reasonable way of saying, this is how I know who the leader is. Because if we have a new leadership election, they cannot be elected using the same ballot number because it's a different proposal. So, all I have to do now is add that leader identifier, the ballot number. So I don't want to use the leader's process ID or something because the leader might gain leadership and then lose leadership and then gain it again. So I can't use the same value there. But if I use that value combined with the proposal number on which they were elected, leader, now I have a unique value. Now I have a way of detecting when the leader changed. And the leadership change is the complicated part of this protocol. It's really easy to see when there's only one leader and they're the ones making the proposals. You send it out, you get the votes back. You send it out, you get the votes back. If you look at the visualizations of this stuff, that is in fact exactly what you will see. It's kind of cool. They have these little web animations and they just bing, and you send out the messages, get the responses back. Send out the messages, get the responses back. And then you can play with them and you can say, well, some of them are going to fail. And the leader's going to fail at a certain rate. And so what you see is things get slower and more complicated around the leadership changes. Because I can't make forward progress on choosing entries in my replicated log when I'm electing a new leader. So I've stratified my decision-making process. I've in essence taken what was a simple protocol and created a second level of that protocol and linked them together. So if I don't know who the leader is, I go back to step one, I elect a leader. We elect a leader, the group elects a leader. Now we have a new leader. Now all we have to do is recover whatever had been decided by the previous leader so that the new leader knows what the state of the system is and we can move forward. That's why that safety is so important. That one edge case where I said, okay, the proposer learns that they've got a proposal that's been accepted by a quorum, but they die at that instant in time and they haven't sent that committed message out, the decision message. They haven't sent that decision message out. It's going to be the responsibility of the new leader to recover that state. And the way that is done depends upon the specific protocol, but the basic idea is that somehow the leader needs to know what the last proposal is that everyone voted for. And then the highest number of proposal he gets back will be the last one that might have been adopted. If I can't verify that there's a quorum, I have to repropose that. Because I need to guarantee there's a quorum. I know this was proposed, but I don't know if it was adopted. But let's suppose that I query and everybody says, oh yeah, it was number 34,579,261 and the value was who? I don't have to go and query. Everybody told me what their last proposal was that they accepted. Now I see that there was a quorum, so I'm done. I don't have to go and say, okay, now I have to propose it again. I could. There's nothing wrong with that. And as soon as I get another quorum, it's the same value. Okay, great. That's fine. And if you read through the paper, this is actually what he ends up describing as part of his implementation. That's what he's telling you. He's saying you adopt a leader, and then the leader makes proposals, and as part of their proposal, they identify the ballot on which they were elected. That way, we've linked our leader and our proposals together in a way that allows us to recover the state of the system if there's a leadership change. But now you can see how the protocol gets complicated around the leadership change. Recovering the state of the old leader from the position of the new leader is what makes this difficult. In your design, this is definitely one of the key issues that you need to be addressing. I can hear the scrambling already, going, oh my gosh, I didn't really think about that one. But you know, still got a couple hours. Raft, PMMC, U-stamp replication, Paxos made simple, fast Paxos, flexible Paxos. What is it? I don't know. Cuddly Paxos. I don't think there is one yet, but I had to make up a name. Every one of these will have some mechanism for recovering that state. That's what makes the Paxos protocol challenging. My goal in walking through this in the way I've done it is to try and make it clear what's actually happening. That's the piece that you need to wrap your head around. The reason that the DS Labs Paxos project is hard is because these failure conditions are really difficult to even think about. Think about how am I going to recover that state? And most people walk in and don't even think about that particular failure and are thus left in a situation where they end up writing their code and it fails the tests. And I actually think that's a bad way of learning what it should have done. Maybe it's the only way you can learn, in which case then you got the code, you can go implement it yourself and play with it. But the reality is you need to think about the problem. You cannot build a system for GitLab by hacking the code together at your keyboard 4 hours before you have to ship it to production. I'm exaggerating. You've got almost 6 hours. The benefit of having an understanding of the problem, design forces you to think about the problem. Well, it's supposed to. You may very well be one of those people who just decided that they could skip it, and that's fine. And it will be more difficult for people to implement your design. I don't know what, did anybody get the high design for Project 1? Paper, that it said high on it. I know some people got it because I saw the reviews. What do you do with that as a design? I mean, well, this is a really easy one for me to review, and it's going to be really hard for me to implement anything. So I'm not sure what I'm going to learn from trying to implement high. Maybe maybe some edibles will do it. Well, they were doing something while they wrote that. I don't know if I think the person who submitted the CPSC 404 actually overwrote it. I didn't see it last time I went through, but I didn't look at everything in gory detail. So there are challenging cases here. This is like the election where different proposers say, I want to be the elector. But what happens when we get different values? Well, so the idea is that send out the proposals, and only one of them is going to get a quorum because we're going to ignore all the lower numbered proposals. And this is really the key to how we handle the racing problem. So the racing problem might lead us to a situation where I can't get a quorum and no one else can get a quorum, in which case then I just make another proposal with a higher number. I can't propose a new value at that stage. If I'm a proposer, remember, I only get to propose that first value. I just get to propose it with a higher ballot number. Eventually, hope that we will get a quorum. Once we have the quorum, we're done. We've adopted our value. No need for anybody else to worry about it. Have our safety, our guarantee. That's our liveness problem. Because if everybody keeps throwing out proposals as fast as they possibly can, we are not going to converge. Well, it's possible that we won't converge. I can't guarantee we won't converge, but it makes it possible that we won't converge. So what Lamport suggests in the implementation is staggering, waiting random amounts of time. If you put some randomness into the system, it solves this problem very quickly. And it doesn't take a lot of randomness, just a little bit of randomness. The network will probably introduce enough randomness in the real world, even if you were like spamming these things out. Eventually, you get a quorum. But we want to get to a quorum quickly, because our goal isn't to try and be obnoxious. Remember, this isn't a Byzantine model. Our goal is not to try and create a denial of service attack. Our goal is to actually get useful work done. So when we are building this thing, us injecting randomness into it is a perfectly reasonable thing to do, and it solves our liveness problem. Multi-Paxos, yes? Okay, when there's a distinguished leader, there's only one source of proposals. They just don't do anything at that. Now, there's an interesting question here that you're not asking, and that is, could I have multiple distinguished proposers? Oh, that's a really good question. I'm glad you asked it. Could you? Do you need to have a distinguished proposer? Why do we introduce this distinguished proposer idea in the first place? Actually, it's an optimization. A distinguished proposer doesn't guarantee he doesn't guarantee liveness. We can get the liveness guarantee that we need just by injecting some randomness into them. The distinguished proposer is mostly about optimization. You see, in a network where proposers are long-lived and the network is stable, having a single leader is actually more efficient. So, having just explained why that might be the popular model to do this, how about if we instead said that what we were doing is we were building a distributed consensus protocol for our drone network that was in hostile territory where it might actually be destroyed, but we needed to make consensus decisions in a fairly short order. I've now created an environment in which the network's not stable, the proposers aren't stable, and yet I still need to have a consensus protocol that works. I would not choose a distinguished proposer in that instance. I would probably choose a different algorithm. I'd probably use basic Paxos, because that would be sufficient. The first actual use of Paxos in a paper of which I'm aware of was the pair of papers. One was called Frangipani and the other one was called Petal. Petal was a replicated disk subsystem. Frangipani was a distributed file system built on top of Petal. And they used Paxos, not multi-Paxos, they used Paxos for the replication. There are actual uses of the Paxos protocol without having a leader. but almost all of the implementations that you see actually do use leaders, specifically because it is generally more efficient in the kinds of network environments we operate in. Question behind. How are the proposal numbers determined again? That is a really good question. I'm curious to see how you answered that in your design document. I suggested a model. I did not give you a definitive answer to how they are to be generated because there isn't a definitive answer. All we know is that the proposers must have unique ballot numbers that are comparable so that I can compare any two proposal numbers and decide which one is less than the other. So in fact, if you actually read what Lamport suggests, he suggests a combination of counter and node ID, which is exactly what he did in the bakery algorithm. I just look at the number on the board and I add 1 to it and I put my number in there. And there I'm guaranteed an ordering because my number is unique. So if you combine some visible number with some number that's unique to you, I can now create an ordering that doesn't require any centralized authority. There are other ways you could do this. So for example, suppose that, let's just take something really simple. So I know that I have 6 proposers. So I agree that I will take every ballot number that starts, modulo 6, 0. You're going to take everything that modulo 6 is 1. He's going to take everything that modulo 6 is 2. And you do it that way as well. So I will do 0, and then I will choose 6, and then I will choose 12. And that would be a monotonically increasing sequence that only relies upon the configuration of the proposers. Don't remember if it's in the paper or not, but he actually talks about how to do what he calls configuration change. Configuration change is where you actually want to change the number of proposers, for example. So if you want to change the layout here, to make this simple to work through in our heads, we said we have a fixed configuration. We can change that configuration. It's very easy to say we don't care about clients in this model. What we care about are proposers, acceptors, and learners. The learners, that one we could probably be pretty fungible about. We could probably change the number of learners without requiring a configuration change. The proposers, it's clear that we need to have a configuration change mechanism if we're going to add a new proposer. The acceptors, whether or not you would need a configuration change depends upon how you have defined a quorum. So for example, if your quorum is just a numerical majority, then yeah, if you add an acceptor or take an acceptor away, you're going to have to change your configuration because your definition of quorum is going to have to change. So I think that in fact, in most models, most cases, it will be the proposers and acceptors that are the critical elements of a configuration. Having a fixed number of these, we now have a simple mechanism for creating things like ballot numbers and whatnot. If you want to change the configuration, you can actually use the Paxos protocol to do that. But you do that using the old configuration, and in essence, the new value you agree to is the new configuration. And the new configuration can't be used until everything that was proposed under the old configuration has been committed. And that's, in essence, we make all the decisions that we can here. We don't make any new decisions under the old configuration. Then we switch to the new configuration. So it's like a it's like a mutex in that instance. We make sure that nothing changes while it's underway, but once we're done, we can switch to that new configuration. And I don't recall if it's in, but I know that he does describe that. A 5-page paper with a lot to it. When you go look at the part-time parliament, I think it's like 28 pages or something. It's long. And some of it is because he's got this whole allegorical style of legislatures and priests and olive contracts. And he's trying Honestly, that's the paper you hand to your humanities friend, and you say, this is what I'm studying, and they might actually get that. Oh, you're an anthropology major, you'll understand this, no problem. Oh, this is cool, this is Greece, this is like olive contracts and priests, and I know all about this stuff. And they'll be explaining it to you. You'd be like, what? I really think that's why Lamport wrote it that way. He was trying to get people to step away from the computer and understand the protocol that was involved rather than understand the mechanics of it. Because you'll notice every time I get into this, it devolves into a discussion of mechanics of how we're going to implement. Multi-Paxos is this optimization where we select a leader and distinguish proposer, leader, view, kind of all the same thing. You can see that there's a lot of similarities between this and view stamp replication. View stamp replication revisited as kind of Liskov coming back and saying, well, there was some good stuff in Paxos, and here we can take our work was predated Paxos. And they can improve that. I mentioned Petal and Frangipani. They both use Paxos. They were, as far as I know, the first actual uses of Paxos, and that's because they were done in the late 90s. Lamport was at Digital Research Center in lovely Palo Alto, California. I don't know, do any of you know where Palo Alto, California is? There's a junior university down the street from Palo Alto. Anybody know that one? Of course. Where are you from? No, but you know California. You were there. For tourism, okay. I actually worked there, so at the Junior U. That's what they call it up in Berkeley. The Leland Stanford Junior University, right? So literally there were 2 research centers that DEC had in Palo Alto. And a lot of the people from Stanford ended up at some point working at one of these. Lamport wasn't from Stanford. He got his degree, his PhD came from MIT. But he was there at the time, and they were talking about this project, and he said, I think I have the protocol for you. And they looked at it and said, this solves exactly the problem that we needed. So they actually used it as part of their work. Google Chubby is an implementation of Paxos. Zookeeper Atomic Broadcast is an implementation of Paxos as well. It's not multi-Paxos. It's Paxos. Paxos is widely used, and this is another one of these nice pictures that I stole from slides from last term, which I borrowed from the slides from Georgia Tech with permission. And it says, so Paxos was published in '98. We see disk Paxos, cheap Paxos, fast Paxos, generalized Paxos, stoppable Paxos, Inkius, vertical Paxos, and ePaxos all through 2013. We have flexible Paxos and fast Paxos, which are more recent than that. I think flexible Paxos is 2018. And I think fast Paxos is like similar time frame. So 2015, 2016. Fast Paxos is interesting in that it requires a larger number of nodes. It actually requires a supermajority to make decisions, but it makes them very fast. It's an optimization. There are lots of research papers on this, including Paxos Made Live, Paxos Made Transparent, Paxos Made Moderately Complex. The last one is the one I mentioned to you. This is the paper that inspired the DS Labs work. I actually find it to be a confusing paper that I had to explain it last term. Part of why I said, I can see why DS Labs is a little confused. It optimizes the Paxos protocol. And in so doing, it makes it harder to understand. Normally, when you are writing code, have any of you ever optimized code at all? The best thing to do is to make it bonehead simple to start off with, and then go back and make it complicated once A, you understand the problem, and B, you know that it needs to be optimized. Have any of you ever written in Python? Nothing in Python is written to be performant. Python is a very powerful language precisely because it takes all of the heavy lifting and shifts it off to code written in C and C++. All of the heavy lifting in Python is done in languages where they're highly optimized. That doesn't make Python a bad language. What it does is it tells you that code optimization isn't actually all that matters here. The real thing they're optimizing in most of these cases isn't the code. What is it? What's the slowest part of this? We got that damn speed of light thing going on. We can only push packets so fast. Why are they looking at optical computing now? It's actually faster. The speed of an electron through copper is what, like 2/3 the speed of light. So it's actually significantly faster. And then we'll provide a performance optimization, performance improvement. So our networks will get faster, but we still have to live with the speed of light, so we still have to focus on the network. I know Java is a weird language, and most people don't pick that because because it runs fast, but it's a very popular language in distributed systems because the performance of the code doesn't matter. And it's portable. As everybody learned, right? You know, the version of Maven that you, Gradle was it? I guess it was Gradle. The version of Gradle that of course, Java code is portable. The Paxos in action animation there that I linked slides is actually cool. It does do a visualization in the web browser and shows you a Paxos protocol, and you can actually send the messages around and see how they kind of overwrite each other. And there's several of these kinds of visuals out there. One that I grabbed, I used it last term as well. And some people find it easier to understand when they have a visualization for it. It will allow you to visualize what the messages in a Paxos do and look like, how the nodes. There you go. Way too much of me talking, way too little of you guys answering questions. But you're probably all burned out because you're working on that design project. Anybody submitted the design project too yet? All right, well, we've got 5 hours and 47 minutes. Yep. Sorry? Oh, you're right. Is it Thursday? No, I thought it was today. Is it Thursday? Oh, all right. Well, then I'm wrong. Whatever it is on Canvas, it is. I thought it was today for some reason. Midnight on Thursday. Oh, no, it's the design report that's due today. You're right. There's too many dates because they all overlap, right? So today is the design report, the implementation report for design project 1, and Thursday, right? I did stagger it specifically because I thought it would be kind of cruel to make you do all of this same deadline. Okay. Yeah, because I remember looking at 5 o'clock and going, I suppose I could stretch that to midnight, but I'll just let them sleep. You're not going to sleep anyway. You're going to go out and like drink pizza and eat beer. All right. Well, thanks very much. If there's no questions, if there are questions, I'm happy to answer them. If there are no questions, then I will see you again next Tuesday. There is no class on Thursday. There is no Thursday class on Thursday. It is Monday, Makeup Monday on Thursday. So make sure you wear your makeup. Clown makeup preferred, of course. Hold on. I'm going to stop the recording.